Hello everybody, this is Anirudh and this is my third presentation for my course in operating systems. As you've seen in the previous two presentations, we worked on the first two projects in the NandToTetris course. We built a variety of universal logic gates, an arithmetic logic unit, worked on combination circuits, and learning from everything that has happened in the first 2 weeks, we built upon that and we come to the third week, which is all about sequential circuits. So up until now, we ignore the issue of time. The input is that they're not changing, and the output is just function of the input, where the output was calculated instantaneously based on different combinations of the input. Plus, the combination logic. And all the Boolean and arithmetic chips that we built so far were combinational, and these functions solely depend on the combinations of the input values. Although they provide important processing functions, they cannot maintain the state. And since computers must not only be able to compute values, they should also be able to maintain the state, preserve data over time, and recall these values. And the act of remembering something is inherently time dependent. Remembers something now that has been committed to the memory before. So in order to build chips that remember the state, we develop some standard means for representing the progression of time. One of the many components that we get to look at is the clock, where in most computers, time is represented by master clock. It is based on an oscillator oscillating between two phases labeled 0 and 1, also known as high and low or tick and tock. And the elapsed time between the beginning of a tick and the ending of the subsequent tock is what we call a cycle. And each clock cycle is modeled as one discrete time unit. And the current clock phase, the tick or the tock, is represented by binary signals 0 or 1, usually on the basis of whether it's low or high. And using the hardware circuitry, we try to broadcast this signal simultaneously throughout the computer using this platform. So there's this hierarchy of sequential chips, the DFFs, the registers, the memory bank, and the counter chips. The DFFs are the most basic of them all. They're the fundamental sequential chip. And on the basis of DFFs, we build registers and memory banks, and both counter chips and memory banks are built on registers. So the DFF, the data flip-flop, is the most fundamental and elementary sequential device. We don't get to build this DFF though, but then all of the other components that we worked on the project, it's all based on the DFF. We've used the DFF everywhere. Thus, the elementary sequential device. So as an input line and output line, it has the function output of t is n of t minus 1. So basically what it does is outputs the input value from the previous time unit, thus remembering the state. And this is used almost everywhere in the coming slides. So the register is a storage device. It can store or remember a variety of data by implementing the classic storage behavior out of t is equal to out of t minus 1, where the output is preserved and sent back to the input. And we can look at it over the diagram over here. This is an invalid design because there's no input for the load bit. For that, we use a multiplex. So we have an input n, and the output is sent back. This generates a feedback loop, and then there's a load bit over here. This is a single bit DFF register. 1-bit register is also called as bit. Now we can construct multiple bit registers. Let's say W bit register from in W binary cell bits. The functionality is both the same, except the equal to assignment over here happens between single bits, and over here it's multiple bits. The same fundamental concept is followed over here. And this is the conceptual random access memory chip. The width and the length can change upon the user's requirements. It's built by stacking a number of registers. It has 3 input lines: the input, the address, the load, and the output. So the basic parameters of this RAM, as I've talked before, the width and the length is all variable. And the address specifies where the register should be accessed at which particular time. In case of a read operation, when the load is 0, the output immediately emits the value of the input. And in case of a write operation, when load is 1, the selected memory commits to the input, which happens the next time unit, which points the RAM to the previous cycle before it starts emitting it. This is a write operation. This is a basic implementation of RAM chip in this course. And as we've talked about before, time matters a lot. And then all the chips that I've described so far are sequential. Sequential chip is one which employs a DFF gate. It's a combinational chip, and you can see in a sequential chip, a DFF gate is sandwiched between two combinational logic circuits. And in its entirety, we call this a sequential chip. And the output is some function of a time, which happens recursively. So out of t is equal to in of t minus 1 and out of t minus 1. And this is the basic output, or the basic output that we get once we have the three input lines for the RAM. The address is a logarithmic function of the n bits. So let's say it's RAM 8. So we have 3 bits over here, and RAM 64. So 64 base 2, log 64 base 2, that's 6. So that's how we calculate the number of RAM chips so that we need an hack platform and compute both read and write operations. This direct access memory unit, which is also called as a RAM. Basically, it's just an array of n-bit registers. We get to look at this while we implement this in the hardware emulator. So in the third project, we are given all the chips that were built in the first two projects, and also the basic fundamental data flip-flop, the DFF. And we build the following chips, starting with a very simple bit all the way to the 16K memory unit, the RAM. So this is a 1-bit register, simple input line, output line, and this is a load bit. So the basic principle of this 1-bit register is when the load bit is 1, you get to load the input and the output emits it, else the output does not emit the input bit. And we build by using a data flip-flop and a multiplexer. The mux takes two input components, the output from the data flip-flop and the input from the register. And also it has a selection line input. And the DFF component, that is, the DFF flip-flop, stores the input value, that is the output of the multiplexer. And it outputs as the DFF, that is in regard to the next clock cycle. So the output of the bit chip is connected to the output of DFF component. With this, you can get the current value of the register. So basically, as we've talked about before, when the load is 1, input is loaded, which becomes the current output. Load is 0, the register does not do anything, that is, it retains its current value. This register is synchronous, it updates its output based on the rising edge of the clock. So we've implemented this in the ID. This is the beat.hdl file. We follow the same principle. When the load is 1, the output is emitted on the previous cycle's input. Load t of 1, then out of t is equal to n of t. Use both the multiplexer and DFF, where the output of the multiplexer is taken as the input in the data flip-flop. So once you modify the code, this is the declaration of the input and output, the implementation part. Once we've completed the code, we can go to the hardware emulator and load the chip as bit.hdl, hardware definition language file. Also load the test script consisting of all of the cases. You can look at one certain case over here. Set input as 1, you set load as 1. There's a tick, you print the output on the top, that indicates the end of the clock cycle. And that keeps on happening for various input and output values. Once we execute this, the execution of this clock bit takes about approximately 107 seconds. Once that is done, you can make sure the format is in binary and view the output. And we have been provided with predefined list of compare files and compare our output to that. And in case there are no changes in our output, we can see that it has been executed successfully. We can view the output. So it follows the principle of the clock bit, where this second column is the load bit. So when the load bit is 0, the state does not change, the output does not change. But then when the load is 1, the output changes to the input of the previous cycle. And compare it. And since nothing has changed, you can say that executed this chip perfectly. So that is what happens when you execute a HDL file for the bit clock. Moving on to the second thing that we're going to execute over here, that's a register. So this is the 1-bit register that we've already done. Based upon this, we built W-bit registers, which are just a combination of various 1-bit registers. Was the same principle of the output function, and we built by multiple 1-bit registers. So it consists of 16-bit chips. They're all connected parallelly. So when the load is 1, the input values from the 0 to the 15. So total 16 bits are taken. and the output reflects the input value. When the load is 0, the current values are displayed, that is, the output remains unchanged. So this is the code for the register. All 16 bits are connected parallelly. And then same function when if the load is 1, then the output reflects the input of the previous cycle. So we declare our input and output variables in the implementation part, and then in the path section, put our code. Use the load output based on different bits that are parallelly connected. And execute this by going to the hardware simulator, loading the register hardware definition language file, register.htl. Also load the script for that, register.pst. Similarly, we have different test case scenarios. We set input as 1. If the load, this is a tick. We provide the output in this talk, end of the cycle. Happens for various scenarios. Make sure the format is in binary and we run the program. Runs for all of these test cases. This HDL file is important from the ID. We made changes to the code that has been provided before, and then we run it using the simulator. So once all of these inputs are executed, we can view the output over here. Follows the same function as the 1-bit clock. So when the load is 1, it shows the state of the previous input line. Load t is 1 and out of t plus 1 is n of t. This principle is followed. And see whenever the load is 1, we get the desired output. We can compare it using the compare file. And since no changes can be found, can say that it has been executed perfectly. So this is how we execute the register file. Moving on, we design different variations of RAM. First, look at the 8 register RAM, and then RAM 8, RAM 64. The basic thing about this is, you can build this RAM device by grouping smaller RAM parts together. First, you build the RAM 8 by grouping a bunch of registers, RAM 64 by grouping 8 RAM 8s, and RAM 512 by grouping 8 RAM 64. I think you get the idea now. So just grouping smaller RAMs, same functionality over here. The 16-bit input line, the 3-bit address input, it specifies the memory location where the read or write has to happen, and the 16-bit output. So it provides in the 8-bit RAM, the module provides the memory with 8 registers. Each one stores a 16-bit value. Load determines whether the input is loaded, which is based on the address input also. And the selected data is emitted from the output after the next time step. These are different variations of the RAM. RAM 8, 64, 16K. Start with simple RAM 8. 8 registers, each 16-bit wide. Out holds the value for a specific register. Out is out 0. Use a 8-way 16-bit multiplexer where all the outputs are put as input lines. We also have the selection as the address line, and the output is generated over here. And the n value that is loaded in the memory section that is specified by the address. So this is the basic skeleton for RAM 8. And go to the hardware simulator, import the RAM 8.htl and also the script file for this. Similarly, we have different test case scenarios. We set load as 1, tick, output talk, again output end of cycle. It happens for all of these case scenarios. These are the internal pairs for different loads, because we've used 8 registers of all of these inputs and the final 16-bit output. And run the program over here. So all of the test cases run, and then we can view the output momentarily for a second over here. Make sure the format is in binary, and we'll just wait for this to complete execution. Once that's done, we can view the output, where all of the 8 registers are used to calculate the final output and compare it using the compare file. Now, out of all the 46 test cases, we can see that there are no changes. It ends with the second column is a load, it ends with 0 load and 3 as the address selection line. Even the compare file is the same. So we can say that it has been executed perfectly. So RAM 64 is the same concept as RAM 8, except here we use 8 registers, here we use 8 RAM 8 chips. Memory of 64 registers, Each are 16-bit wide. Output holds the output value. Out 0, all of this is used again in an 8-way 16-bit multiplexer. Selection is the address line for all of this 3rd to 5th bit, and the output can be viewed in the final out is equal to out. Loaded value will be emitted to out after the next time step to make sure that happens properly. And the in value is loaded based on the memory location, which is specified by the address. This is the output. This is the basic outline of a RAM 64 file. Same thing except we use 8 RAM 8 chips. Load the HDL file. The script file as well. RAM 64 TST. Run the program. So it's clocked over here, and then we make sure the format is binary. Runs for all of these test cases. Happens to take one. 8 RAM 8 chips. First we use the demultiplexer and then the multiplexer at the end. Demux 8-way, multiplexer 8-way. And the output is loaded in the out variable. So once all of the execution is done, and view the output. Make sure the format is binary. View output. All is the same principle. It's built upon 8 RAM 8 chips. The load is 1. You get the output as the previous cycle's input. The various address bits also, in which the input bit is loaded. Load varies from 0 to 1. Then compare it to the desired output. And since nothing changes, you can say that this is run perfectly. Moving on to RAM 5 and 2. Similarly, based on what we've looked on at RAM 64, RAM 500 does the same thing, except now it's 8 RAM 64 chips. Each has its own address line. The out, all of the 7 outputs, we put it in the 8-way multiplexer. And then it's low. First, we load it into the demultiplexer. And the loaded value is emitted to the out after the next time stop. So selection line of all of the addresses. The outputs are put in the 8-way multiplexer. Similar functionality, same principle as the previous 64 and 8 RAMs. This is bigger size. So we load the chip for RAM 5 and 2. It's in a different directory. RAM 500 actually. For this script file. And run for different test cases where we set address differently, we set load bits differently. There's a tick and talk, ending and starting of different clock cycles. All these load bits, and basically 8 RAM 64 chips, based on which we get the RAM 5 and 2. Runs for about approximately 85 seconds. Once that is done, 81 seconds, we make sure the format is in binary via the output. Same, the input is based on the memory line that is obtained from the address. The load is 1. Load is 1, the input is loaded and it's displayed in the output section. It's memory of 512 registers, each is 16-bit wide. So we can compare it to the compare file. And since nothing changes, we can say that it has run perfect. Moving on to RAM 4K. It's memory of 4K registers. Similarly, each 16-bit wide out holds the value specified by the address that we get from each of these 8 RAM 512 chips. Used 8 RAM 64 chips before, now we use 8 RAM 512 chips. Different load values for each of them, and the outputs are all put in an 8-way 16-bit multiplexer. The in value is loaded into memory location that is specified by the address, and the loaded value will be emitted in the output variable after the next time step. Same functionality, RAM 4k.hdl. You can load the HDL file. Logged 4k RAM and also the test script. Once we do that, we can run the file for different scenarios similar to the previous to 64 and 512 versions of the memory. And see different values changing based on the inputs that are given in combinations. See the load bits keeps changing based on each iteration. Wait for it to complete execution, approximately 80 seconds again. View the output. Follows the same principles as previous rounds. The size changes. Compare it to the same people, and since there's no pop about any changes, you can say that has executed perfectly. Going on to the last and final, the biggest version, RAM 16-bit. Now, in the previous version, we've used 8 RAMs. Here we just used 4K RAM chips. It's a memory of 16K registers. Again, it's 16-bit wide. Output holds the value. Stored at the memory location provided by the address in the selection line. Load is 1, then the in value is loaded at the memory location that is specified by the address. And it will be emitted after the next time step. Declare the variables in same fashion we proceed for RAM 16K. So input the 16K HDL file. Also the test script to make sure all of the cases are properly. And we run the code. This also takes a bit and look at all the different outputs changing over here. It's 4 RAM, 4K chips, same principles. 16-bit input line and 16-bit output as well. See various output bits changing. The first, second, third, and fourth, 0, 1, 2, 3. Runs for over 81 seconds. And view the output. And check if it has been executed properly, you can compare it. If nothing changes, and say that it has been executed properly. So it started all the way from the first bit.hdl. That bit will build a register. From 8 registers, we built a RAM 8. From 8 RAM 8, we built a RAM 64. From 8 RAM 64, we built a RAM 512. And then from 8 RAM 512, we built RAM 4K. And then from 4 RAM 4K, we built RAM 16K. Each using a demultiplexer and a multiplexer. Functionality remains the same for all of them. So, as I've said, you can build it by grouping smaller RAM parts together. So this is all about implementation of the random access memory in the hardware emulator. Going on to the last circuit that we've implemented as a program counter. This is built from a register, an incrementer, and some basic logic gates. It has the input lines, load, increase, and reset line, and 16-bit output as well. So the 16-bit input, it is loaded when the load is active. Load is a control signal. When the load is 1, counter loads the value from the input. INC is an incremental control signal. When INC is 1, the counter increments the value by 1. The reset is a reset control signal. When the reset is 1, the counter resets the value to 0. And the output is the current value of the counter. So this function is a 16-bit counter. When the reset is active, counter resets it. When the load signal is active, you load the input. The incrementer is active, you increment the bit by 1. You can view it all in the output section. This is the code for a program counter. Use an incrementer, the multiplexers, and a resistor. As I've said before, use the basic logic gates, combination circuits, and the resistor, where the input is the output of the previous multiplexer. So you can see this fashion like following: the output input for the second multiplexer is the output of the first multiplexer that keeps on happening in this sequential logic. Declare the inputs, the output, and you can view the output in the outer window. So this is a function. If reset is 1, out of t plus 1 is 0. Load is 1, that is when load is active. Out of t plus 1 is equal to n of t. An incrementer is active. Out of t plus 1 is equal to out of t plus 1. That is integer addition. We add 1. That is incrementation. Else out of t plus 1 is equal to out of t. There is no change in state. So we can import the program counter file pc.hdl. Same code. You can use a script as well, pc.txt. And we can run the program. Runs for all of these test cases where the different values for load, input, and output. Once that is done, we can view the output. 15 cases, load is 1, increment is 1, follows these principles. And once that is done, we can compare it to the output, and since nothing changes, the output that we've gotten is equal to the desired output, so it has done perfectly. So this is all about the program counter. And with this we come to the conclusion for the third project. It started with building a bit, and then from that all the way down to 16K RAM, starting from the smallest unit to the biggest 16K memory unit. We also built a program counter. And this is how we've implemented sequential software in the hardware emulator in the NandToTetris course. I'm excited to see where this course takes me next, and I hope this has been information. Thank you very much.